Hello, friend. Tonight, the world outside might be loud, or maybe it's just your thoughts that won't settle. Either way, you're here now, and that's enough. Some nights the sky feels closer than it should. Stars breathe slower. Silence folds around itself. Maybe that's just the mind learning to listen again. There's a photograph you should know about. It was taken in 1990 from the edge of everything we'd ever touched. In it, Earth appears as a single pixel, pale blue, impossibly small, suspended in a beam of scattered sunlight. When Carl Sagan saw this image, he wrote words that still echo. Everyone you love, everyone you know, everyone you ever heard of every human being who ever was, lived out their lives on a mote of dust, suspended in a sunbeam. But here's what makes the heart pause. That photograph wasn't taken by human hands standing on some distant shore. It was taken by a machine we built in 1977. A machine that's still out there, still moving, still speaking into the dark. A machine named Voyager. Tonight we're going to drift alongside the loneliest travelers humanity ever made. Before we begin, if you find comfort in these quiet journeys through the cosmos, you might like to stay a while. You can gently tap the like button, not for noise, but as a quiet nod between us. Subscribe if you'd like more stories, told softly, and ring the little bell so the next quiet night can find you again. These small gestures help more stories like this find their way to others who need them. Now, let's drift. Voyager 1 and Voyager 2 launched in the summer of 1977, when the world was different. Disco played on radios. The Cold War hummed in the background. Nobody had personal computers. Nobody knew what the internet would become. But NASA knew something else. The planets were aligning in a way they wouldn't again for 176 years. Scientists call it the Grand Tour alignment, a celestial arrangement where Jupiter, Saturn, Uranus, and Neptune would line up like stepping stones across the outer solar system. This alignment happens roughly once every 2 centuries. If you miss it, everyone alive during your lifetime will also miss it. Your children will miss it. Your grandchildren will miss it. The mission planners understood some windows open only once. Think about that for a moment. How many windows have opened in your own life? Moments when everything aligned just right, when the path forward seemed almost illuminated. And how many did you walk through? How many did you watch close? The Voyager missions were built on a gamble. Not a reckless one, but the kind of gamble that says, we may never get this chance again, so we'll build something that lasts. Each spacecraft weighed about 825 kilograms. Each carried 11 scientific instruments. Each held a golden record, a literal phonograph disc, plated in gold containing sounds and images from Earth. Music, greetings in 55 languages, a baby crying, wind, rain, thunder, the human heartbeat. It was a message in a bottle cast into an ocean that has no shore. But here's what's easy to miss. The Voyagers weren't designed to find anything. They were designed to look. There's a difference. One is about arrival, the other is about attention. When Voyager 1 launched on September 5th, 1977, actually, let me correct that. Voyager 2 launched first on August 20th. Voyager 1 launched 16 days later, but on a faster trajectory. The names don't follow the order of departure. They follow the order of arrival at Jupiter. Even in naming, we were thinking ahead to what these machines would see. The journey began not with fire and thunder, though there was plenty of that. The Titan Centaur rocket produced a thrust of over 2 million pounds. But the real beginning was quieter. It was in the calculations, the orbital mechanics, the realization that you could use a planet's gravity not as a barrier, but as a slingshot. This technique, called gravity assist or gravitational slingshot, wasn't new in 1977. It had been theorized, tested on earlier missions like Mariner 10. But Voyager would perfect it. As the spacecraft approached Jupiter, it would fall into the planet's gravitational well, accelerating as it fell like a stone dropping into a valley. But Instead of crashing, Voyager would whip around the planet's far side and be flung back out faster than it arrived. Jupiter wouldn't slow down, not in any way we could measure. The planet masses 1.878 x 1027 kilograms. Voyager masses 825. The exchange of momentum was real, but invisibly small, like a child borrowing speed from a freight train by holding onto it for half a second. Yet that borrowed speed was everything. It meant Voyager didn't have to carry enough fuel to accelerate on its own. It could lean on the universe itself. There's something worth pausing on here. We often think of strength as what we carry, the fuel we store, the energy we hold in reserve. But the Voyagers teach something else. Strength can also be knowing what to borrow, knowing when to let the current carry you. How much energy have you spent pushing against gravity when you could have used it? The spacecraft were built to survive what nothing human-made had survived before. They would pass through Jupiter's radiation belts, a storm of charged particles so intense it's like standing inside a nuclear reactor. They would endure temperatures swinging from 300 degrees Celsius in sunlight to -200 in shadow. They would travel so far from the sun that solar panels would be useless. Instead, they carried plutonium-238 power sources, radioisotope thermoelectric generators that convert heat from radioactive decay into electricity. Even now, nearly 50 years later, those power sources still hum. Fainter, yes. The output has dropped from 470 watts at launch to about 249 watts today, but still enough to send a signal home. A signal that takes over 22 hours to reach us from Voyager 1. 22 hours traveling at the speed of light, covering 15 billion miles. When we send a command to Voyager, we're speaking to where it was yesterday. When it answers, we're hearing from where it was 2 days ago. Conversation at that distance becomes something else. It becomes faith. The golden record is perhaps the most quietly optimistic thing our species has ever made. Not because we truly believed someone would find it. The odds are so small they barely exist. Space is vast in a way that language fails to capture. The nearest star system, Proxima Centauri, is 4.24 light-years away. Voyager 1 is currently moving at about 38,000 miles per hour. At that speed, it would take over 73,000 years to reach Proxima Centauri if it were headed in that direction, which it isn't. In about 40,000 years, Voyager 1 will drift within 1.6 light-years of a star called Gliese 445 in the constellation Camelopardalis. By then, human civilization will either be unimaginably transformed or long gone. The record will still be there, spinning through the dark. The record's golden cover is designed to last 1 billion years, longer than our species has existed. Longer than most of the species that have ever lived on Earth. The instructions for playing it are etched onto the cover, a diagram showing how to extract the stylus, how fast to spin the disc, how to decode the images. We sent instructions for a technology that may be obsolete before the record encounters anything capable of reading it. But maybe that's not the point. Maybe the point is that we said something, that we took our loneliness and turned it into a gesture. Hello, we said in 55 languages. Hello from the children of planet Earth. In Sumerian, one of the oldest written languages we've ever deciphered, now dead for over 2,000 years. The record says, "Greetings to you, whoever you are. We come in friendship to those who are friends." A dead language speaking to no one from a species that might itself become a dead language before the message is ever received. And somehow, that's not sad, it's tender. The golden record contains 116 images. The first is a circle a calibration mark to help decode the others. The next images show mathematical definitions, then the solar system, DNA structure, human anatomy, a fetus, a diagram of conception and birth, which caused no small amount of controversy in 1977. Some felt it was too explicit, though it's purely scientific. But then we've always been strange about our own bodies. There are images of people eating, drinking, demonstrating tools. A man licking an ice cream cone, a gesture so specific, so human, it becomes almost unbearably poignant. Somewhere in the record is a supermarket, a traffic jam, the Great Wall of China, the Taj Mahal, a string quartet, and sounds of mother kissing her child. Footsteps, laughter, a fire crackling, Morse code spelling out per aspera ad astra through hardships to the stars. The music begins with Bach the Brandenburg Concerto No. 2, a piece so mathematically elegant it feels like it should exist independent of us. Then comes Beethoven's Fifth Symphony, Stravinsky Chuck Berry's Johnny B. Good. There's a Navajo night chant, a Peruvian wedding song, Bulgarian folk music, the chant of a pygmy girl's initiation ceremony. Blind Willie Johnson's Dark Was the Night, Cold Was the Ground is on that record. Johnson recorded it in 1927, a wordless slide guitar hymn that sounds like loneliness made audible. He died in 1945, poor and nearly forgotten. Now, his music is traveling through interstellar space, carried by a machine that will outlast everything he ever knew. The record also contains brainwaves the electrical patterns of a woman named Anne Druyan, who would later marry Carl Sagan. She meditated for an hour while hooked to an EEG machine, thinking about human history, about love, about the absurdity and beauty of existence. Those thoughts were encoded as sound. Somewhere between the stars, a record carries the electrical echo of human consciousness trying to make sense of itself. Can you imagine what we were saying? Not just with the words, but with the choices we sent Bach and Chuck Berry. We sent greetings in Sumerian and modern Mandarin. We sent the sound of a human heartbeat. 120 beats per minute, the rhythm of a species that evolved under a yellow sun on a small wet planet in an ordinary spiral galaxy. We sent the parts of ourselves we hoped were true. The Voyagers carry no weapons, no territorial claims, no advertisements. They're not fast by cosmic standards. A snail could cross the room faster relative to its size. They're not particularly intelligent. Each has less computing power than a modern hearing aid. They can't learn, can't adapt beyond their programming. They're fragile in the way all human-made things are fragile. But they're still out there, still functioning, still turning their instruments toward whatever light remains. And in that, there's something that feels like a promise we made, though we didn't know we were making it. A promise that we would reach, that we would try to understand, that we would look beyond ourselves, even knowing we might never see what's looking back. Have you ever sent a message you knew wouldn't be answered? Not out of hope, really, but because the act of sending mattered more than the reply. The Voyagers are that message. Permanent and weightless, fragile and eternal. They speak not because they expect to be heard, but because silence felt impossible. Two machines no bigger than a car, carrying everything we couldn't say in any other way. Carrying the sound of rain, carrying a mother's kiss, carrying the mathematics of music and the music of mathematics. They won't stop. Even when they go silent, when the last watt of power fades and the instruments finally sleep, the spacecraft will keep moving. Their trajectory is set. In the vacuum of space, there's nothing to slow them down. No friction, no resistance, just motion and time and the long dark between stars. And maybe that's the most human thing we've ever done. Not the building, not the launching, but the refusal to let distance mean the end of speaking. We're still here, the Voyagers say. We were here. We looked up and wondered, and we're still listening for the echo. But before we listen, we have to understand what they saw. What they witnessed that changed how we see ourselves. The journey didn't begin with the photograph from 6 billion kilometers away. It began much closer. It began at the first planet to fill their cameras with impossible color. It began at a storm that's been raging since before any human looked up at the night sky and wondered what those lights were. It began at Jupiter. There's a storm on Jupiter that's 3 times the size of Earth. It's been spinning for at least 190 years, maybe longer, maybe 350 years or more. Nobody knows when it started. It was already ancient when the first humans saw it through telescopes. It's still there now, turning slowly, a vast wound in the atmosphere that refuses to heal. When Voyager 1 arrived at Jupiter on March 5th, 1979, followed by Voyager 2, that July, they didn't just photograph the storm, they watched it breathe. They measured its winds, its depth, the way it pulls clouds into itself and spits them back out. They saw something we'd only glimpsed from Earth. The storm wasn't just big. It was alive in the way weather can be alive, self-sustaining, chaotic, indifferent. The Great Red Spot, they call it. Though great feels insufficient. And red isn't quite accurate either. It's more brick-colored rust orange fading to salmon at the edges. Colors that shift, depending on what chemicals are churning up from below: ammonia, ice, phosphorus compounds, sulfur lifting from deeper layers we still can't see. The storm rotates counterclockwise, completing one full turn every 6 Earth days. Winds at its edge reach 432 kilometers per hour, faster than the strongest tornadoes ever recorded on our planet. And unlike Earth's storms, which die when they hit land or lose their heat source, Jupiter's storm has no land to hit. No friction to slow it, just endless bands of cloud feeding it, sustaining it. Scientists suggest the storm is essentially a high-pressure system, trapped between jet streams, massive rivers of wind that flow in opposite directions above and below it. The jet streams act like walls containing the storm, preventing it from drifting or dissipating. It's locked in place, spinning in the same region of Jupiter's southern hemisphere, where it's spun for centuries. A rage that geography won't let end. Think about that. A storm so old that when it began, most of your ancestors weren't born yet. A fury sustained not by fresh anger, but by the shape of the world around it, by currents and pressures that won't let it go. How many of us carry storms like that? Old anger's old hurt spinning in the same place year after year. Not because we feed them, but because the shape of our inner world won't let them dissipate. Voyager revealed something else about Jupiter. The planet isn't quiet, it roars. Jupiter's magnetosphere, the region of space dominated by its magnetic field, is the largest structure in the solar system. If we could see it with our eyes, it would appear bigger than the full moon in our sky, even from Earth. The magnetic field is 20,000 times stronger than Earth's generated by an ocean of liquid metallic hydrogen deep inside the planet, a substance that exists nowhere naturally on Earth because we don't have the pressure to create it. This magnetic field traps charged particles, electrons, ions, creating radiation belts so intense that Voyager's instruments were nearly overwhelmed. The radiation levels were worse than standing unshielded in the core of a nuclear reactor. Engineers had built the spacecraft with extra shielding, extra redundancy. But even so, some instruments flickered. Some data streams went strange for hours. Jupiter was testing them, testing whether these small machines from a small planet could withstand the violence at the heart of something vast. They survived. Barely, but they survived. The cameras captured lightning in Jupiter's clouds, superbolts, some of them thousands of times more powerful than lightning on Earth. The storms that generate this lightning are wider than continents. Some scientists believe the lightning might create organic molecules in the upper atmosphere, complex carbon compounds falling like chemical rain into the deeper layers below. Life probably doesn't exist in Jupiter's clouds. The conditions are too harsh, too chaotic. But the chemistry of almost life might be there, forming and dissolving in the turbulence, never quite assembling into something that remembers itself. Does that make you wonder? How many times did the chemistry of almost life form on Earth before life finally took hold? Voyager also saw Jupiter's moons in detail for the first time. 4 large ones: Io, Europa, Ganymede, Callisto, discovered by Galileo in 1610. He called them the Medicean stars, trying to flatter his patrons. History renamed them for Jupiter's lovers in Roman mythology, which feels both poetic and uncomfortable given the stories. But it was Io that stopped everyone. On March 8, 1979, 3 days after Voyager 1's closest approach to Jupiter navigation engineer, Linda Morabito, was examining images to track the spacecraft's position. She noticed something strange at the edge of Io, a plume and umbrella-shaped cloud rising 280 kilometers above the moon's surface. It wasn't a cloud. It was a volcanic eruption, active volcanism on a moon. Nobody had predicted this. Earth and Io are the only two bodies in the solar system where we've confirmed active volcanic eruptions happening right now. But Io's volcanism is nothing like Earth's. The moon is the most volcanically active body we know. Its surface is young, constantly resurfacing itself with sulfur and silicate lava. Some plumes shoot material 300 kilometers into space, higher than the International Space Station orbits Earth. The heat source isn't radioactive decay like Earth's interior. It's tidal heating. Jupiter's gravity pulls on Io. Europa pulls. Ganymede pulls. These gravitational tugs stretch and squeeze Io's interior, flexing it, heating it through friction. The moon is essentially being kneaded like dough, and the heat generated is enough to melt rock. Io can't escape. Its orbit is locked. The forces pulling on it won't stop. So it burns perpetually, a small world caught between larger powers. There's a kind of cruelty in that, though of course the universe doesn't intend cruelty. It just is. But when you look at Io's surface yellows and oranges and reds, sulfur compounds painting it like a bruise, it's hard not to see a body shaped by forces it never chose. Europa, by contrast, is ice. Smooth white, crisscrossed with reddish-brown cracks like veins under skin. Voyager's images showed a surface almost devoid of impact craters, which means the surface is geologically young, maybe only 40 to 90 million years old. Something is resurfacing Europa. Something beneath the ice. Scientists now believe Europa has a subsurface ocean liquid water, kept warm by tidal heating, similar to Io's, though less extreme. This ocean might contain twice as much water as all of Earth's oceans combined, hidden under an ice shell 15 to 25 kilometers thick. We don't know if anything lives there. We have no way to know without going back drilling through the ice, sending something down into the dark water below. But the chemistry is possible. The energy is there. The time has been there billions of years. If life exists anywhere in our solar system beyond Earth, Europa is where many scientists would bet on finding it. Voyager couldn't tell us that for certain. It could only show us the cracks, the smoothness, the strangeness of a moon that doesn't look dead. Sometimes that's all we can do, point at something and say, look at what might be hidden. Ganymede is the largest moon in the solar system, bigger than the planet Mercury. It has its own magnetic field, the only moon known to have one. Callisto is ancient crater geologically dead, a museum of impacts stretching back 4 billion years. And then there are the smaller moons, dozens of them, some discovered by Voyager. Tiny, irregular captured asteroids, perhaps orbiting in strange elliptical paths. Amalthea reddish and potato-shaped, orbiting so close to Jupiter, it's slowly spiraling inward, thousands of years. From now it will break apart, adding its mass to Jupiter's ring. Yes, Jupiter has rings. Thin, faint, made of dust, knocked off the inner moons by micrometeorite impacts. Voyager 1 discovered them by accident, pointing its camera back at Jupiter after catching the rings backlit by the sun. They're so faint, we'd never seen them from Earth. They don't look like Saturn's rings. There's no grandeur, no sweeping arcs. Just a whisper of dust, a reminder that even gas giants wear halos. The images Voyager sent back took 40 minutes to reach Earth. 40 minutes at the speed of light. By the time scientists saw what Voyager was seeing, the spacecraft had already moved on, already turned its instruments toward the next target. This is what exploration at that distance requires: trust. You can't steer in real time. You can't react. You program the mission, release it into the dark, and wait to see what comes back. It's the opposite of control. It's faith in what you built and faith in the mathematics that say, if we do this, we'll end up there. When Voyager 1 left Jupiter's system, it used the planet's gravity to accelerate towards Saturn, stealing a tiny fraction of Jupiter's orbital momentum. Jupiter slowed by an amount so small, it's unmeasurable about 1/1,000,000,000th of a kilometer per billion years. Voyager sped up by 10 kilometers per second. The universe allows this, lets the small borrow speed from the vast, doesn't demand payment, doesn't even notice. What would change if we lived like that? If we understood that accepting help, borrowing momentum from something stronger, doesn't diminish anyone. The Great Red Spot is shrinking. Observations over the past century show it getting smaller, though nobody knows why. In the 1800s, it spanned 40,000 kilometers across. Now it's about 16,000. It might disappear entirely within our lifetimes. Or it might stabilize. Or it might collapse and reform the way storms do. Even ancient things end. Even furies that seemed eternal. There's comfort in that, and also sadness. The storm has been a landmark, a feature we could point to and say there, that's Jupiter. When it's gone, the planet will still be vast, still beautiful, still rotating every 10 hours with bands of cream and brown and rust. But something will be missing, a scar that finally healed. Do we mourn the end of old pains? Or do we celebrate that even the deepest wounds can close? Voyager didn't answer these questions. It just showed us the storm, measured it, watched it turn. It sent back numbers and images data that scientists are still analyzing decades later. Every few years, someone publishes a new paper about Jupiter's atmosphere, about the chemistry in the clouds, about the way heat moves through layers we can't directly see. The mission ended 45 years ago, but the data keeps teaching. The spacecraft moved on, carrying its golden record, carrying its plutonium heart, carrying the faint echo of everyone who built it and everyone who hoped it would survive. It left Jupiter behind that massive world with its storms and moons and radiation, and turned toward the next encounter, toward rings that look like memory, toward a planet wearing its past like jewelry, delicate and broken and impossibly beautiful, toward Saturn, the jewel of the solar system, where Voyager would see something no human eye had ever witnessed, a place where chaos and order dance together, where the mathematics of gravity create art across hundreds of thousands of kilometers of space. But we're not there yet. We're still in the space between planets drifting through darkness, waiting for the next light to fill the cameras. And in that waiting, there's a kind of peace, the knowledge that something waits ahead, that the journey isn't finished, that we built something capable of traveling farther than we could follow, but we follow anyway with radio dishes and patience, listening across the emptiness for the signal that says still here, still moving, still looking. If you could gather all the fragments of everything you've ever lost, every forgotten moment, every scattered piece of who you used to be, and arrange them in a circle around yourself, what would that look like? Saturn knows. When Voyager 1 reached Saturn on November 12, 1980, followed by Voyager 2 in August 1981, the spacecraft didn't just see rings. They saw structure, order, hidden inside chaos. Billions upon billions of individual pieces, ice chunks, dust grains, boulders the size of houses, all orbiting together in bands so precise they look designed. From Earth, the rings appear solid, smooth, elegant. Galileo saw them in 1610 and thought Saturn had ears. His telescope wasn't strong enough to resolve the true shape. He wrote in Latin in an anagram he could decode later, "I have observed the most distant planet to have a triple form." 2 years later, he looked again, and the rings had vanished. Saturn's axial tilt had turned the rings edge on from our perspective, making them invisible. Galileo died confused, never knowing what he'd seen. It wasn't until 1655 that Christian Huygens proposed the truth: Saturn was surrounded by a flat ring. In 1675, Giovanni Cassini discovered a gap in the rings, a dark band separating them into distinct sections. We call it the Cassini division, now named for the man who first saw the emptiness between. But Voyager revealed the rings weren't simple. They weren't even rings plural. They were thousands of ringlets braided, twisted, knotted, some barely a few meters wide. The main rings, A, B, C, contain structures within. Structures density waves, bending waves, propeller features, where small moonlets clear paths through the ice. The F-ring just outside the main system appears twisted like a rope with clumps and strands that seem to tangle and untangle over time. Scientists suggest these structures are shaped by resonances, gravitational nudges from Saturn's moons that occur at mathematically precise intervals. When a ring particle orbits Saturn exactly twice for every once a moon, orbits it feels the moon's gravity in the same place every orbit. These nudges add up, push particles closer together, or pull them apart, creating gaps, waves, patterns, chaos organized by rhythm. The rings are mostly water ice, frozen water, from the same hydrogen and oxygen that flows in our blood. Some particles are pure ice, clean and bright, reflecting 80% of the sunlight that touches them. Others are darker, stained with dust. Organic compounds, maybe silicates from ancient asteroids that wandered too close and shattered. Most ring particles are small, centimeters, pebble-sized, but some are enormous, several meters across, tumbling through the swarm. Voyager's instruments detected everything, building a statistical picture of size distribution. And here's what they found. The rings are fragile. Most particles never touch. They're spread out, separated by empty space held in formation by gravity and angular momentum. From far away, they look solid. Up close, they're mostly absence. Isn't that true of most beautiful things? That they're held together more by what's between them than what's there. The rings are thin, astonishingly thin. They span 282,000 kilometers from inner edge to outer edge, roughly 3/4 the distance from Earth to the Moon. But their thickness in most places only 10 meters, in some regions even less. If you scaled the rings down to the thickness of a piece of paper, they'd stretch wider than a football field. Imagine that. A structure vast enough to swallow multiple Earths, yet so delicate you could walk through its thickness in a dozen steps. Voyager discovered that Saturn, like Jupiter, has a powerful magnetosphere. But where Jupiter's is violent and chaotic, Saturn's feels almost gentle-shaped, scientists believe, by the rings themselves. The rings absorb charged particles, act as a drain for the radiation belts, keep the inner magnetosphere cleaner than it would otherwise be. The rings protect Saturn from its own power, quietly, without ceremony. There's a gap in the rings, called the Cassini division, 800 kilometers wide, easily visible from Earth with a small telescope. For centuries, people thought it was empty. Voyager proved otherwise. The gap isn't empty. It just has fewer particles, lower density. Light passes through more easily, so it looks dark compared to the bright main rings. Even emptiness has texture. The A ring contains the inky gap, a narrow band 325 kilometers wide. And inside that gap, Voyager found a tiny moon pan, just 35 kilometers across, shaped like a walnut. Pan orbits within the gap, and its gravity sweeps the space. Clean pushes particles to either side, maintains the boundary through nothing but its presence. A small thing creating order just by being where it is. Scientists still debate how old the rings are. Some models suggest they're ancient formed. When Saturn formed 4.5 billion years ago, remnants of the same cloud of gas and dust that built the solar system. Other evidence suggests they're young, geologically speaking, perhaps only 100 million years old. Created when a moon or comet wandered too close and was torn apart by Saturn's gravity. There's a boundary called the Roche limit, the distance inside which tidal forces will shred any object held together only by its own gravity. For Saturn, that limit is about 147,000 kilometers from the planet's center. The rings orbit entirely within this limit. They exist in a space where nothing whole can survive. Does that resonate? How many of us live in spaces where we feel constantly pulled apart, where staying intact requires more energy than we have? Voyager also showed us Saturn's moons in detail. Titan, the largest, bigger than Mercury, wrapped in a thick orange atmosphere of nitrogen and methane. Enceladus, tiny and bright, with geysers of water vapor shooting from cracks at its south pole. Scientists now know there's a subsurface ocean beneath that, ice warmed by tidal heating, possibly containing organic chemistry. Mima's cratered so heavily it looks like the Death Star, with one impact so large it nearly shattered the moon entirely. And then there are the shepherd moons, Prometheus and Pandora, flanking the F ring, their gravity shaping it, braiding it, keeping it confined. Without these moons, the F ring would spread, dissipate, fade into the background darkness. But they hold it together, these two small bodies, pulling and pushing in a dance they have maintained for millions of years. Sometimes structure requires tension from both sides. The Voyager team made a discovery that still puzzles scientists. Spoke features in the B ring, dark radial bands that appear and disappear over the course of hours. They rotate with the rings, but also seem to form independently aligned along Saturn's magnetic field lines. The leading theory involves electrostatics dust particles levitating slightly above the ring plane, charged by ultraviolet light or plasma, held aloft by electromagnetic forces. These particles cast shadows, creating the spokes. But why they form, why they vanish, the exact mechanism, it's still not fully understood. Even after decades of study, the rings keep their secrets. Voyager measured the rings with occultation experiments, watching starlight pass through them, measuring how the light dimmed and brightened as different structures passed in front of the star. Like reading Braille, each flicker of light encoded information, particle density gap, locations, ring thickness. From these flickers, scientists built maps. They found that some gaps are resonances with known moons, but other gaps have no obvious cause. Empty spaces that shouldn't be there according to the models. Ghosts in the data. Sometimes absence speaks louder than presence. The rings are not permanent. They're losing mass slowly, constantly. Ice particles collide, chip fragments off each other. Some fragments spiral inward, fall into Saturn's atmosphere, burn up in the clouds. This process, called ring rain, adds somewhere between 432 and 2,070 kilograms of water to Saturn's upper atmosphere every second. The rings are dying, dissolving, flowing into the planet like memory, fading into sleep. Scientists estimate they might only last another 100 million years, maybe less. In cosmic terms, that's brief. If intelligent observers had evolved on a moon of Saturn 1 billion years ago, they would have seen a naked planet. If they evolve 1 billion years from now, they'll see the same. The rings are temporary, a phase, a moment of beauty that happens to overlap with our moment of watching. Does that make them more precious or less? Voyager 1 flew within 124,000 kilometers of Saturn's cloud tops. Close enough to see details in the atmosphere, bands of color storms, smaller and paler than Jupiter's, but still there, still churning. Saturn rotates quickly, once every 10.7 hours, and this rotation winds up to 1,800 kilometers per hour at the equator, faster than Jupiter's, faster than anything on Earth. But Saturn's atmosphere is gentler than Jupiter's in appearance, cream and gold and faint ochre. A muted palette. The clouds contain less ammonia, less chromophore chemistry to paint them vivid. It's as if Saturn saves all its drama for the rings, keeps the planet itself understated. Voyager 2 followed 9 months later, taking a different trajectory, flying closer to some moons, farther from others, filling in gaps in the data. Between the two spacecraft, humanity saw Saturn's system in 3 dimensions. For the first time, not just one perspective, but multiple angles, multiple seasons. And what they saw was fragility, beauty made from brokenness, order arising from collision and gravity and time. The F-ring is chaotic but not random, braided but following rules. Scientists traced its structure and found that small moonlets too tiny to see, individually orbit within the ring itself, creating wakes, clearing lanes, shepherding streams of particles into new configurations. The ring changes, year to year, decade to decade. The Cassini mission, which arrived at Saturn in 2004, compared its observations to Voyagers and found differences. New structures, vanished features. The rings are not static. They're alive in the way weather is alive, always moving, always becoming. Memory works like that too, doesn't it? We think of memories as fixed, recorded, permanent. But every time we recall something, we change it slightly. We add new context, subtract details that no longer fit. Our past rearranges itself, constantly shaped by the gravity of who we are now. The rings are made of fragments, but they're also made of space, of the distances between fragments. And it's the spacing that creates the structure too close, and everything collides, merges, loses definition. Too far, and nothing holds together. There's a lesson there, though, maybe too obvious to speak aloud, about how relationships work, how communities work, the necessity of distance, the art of orbiting near enough to matter, but far enough to remain whole. Voyager didn't linger at Saturn. The trajectory was already set using Saturn's gravity to accelerate onward deeper into the outer solar system. Voyager 2 aimed for Uranus and Neptune. Voyager 1 aimed up out of the ecliptic plane, beginning its long climb away from the plane where planets orbit. As the spacecraft left, their cameras turned back. One last look. The rings from behind, backlit by the sun, glowing like frosted glass. In that geometry, structures invisible from the front became visible, faint rings, dust bands. The E-ring, a broad, diffuse torus, fed by Enceladus's geysers, particles of ice suspended in space. Even what seems empty has something in it if you change your angle. The images took 90 minutes to reach Earth. 90 minutes of waiting while the data traveled at light speed across 1 billion kilometers. By the time scientists saw what Voyager saw, the spacecraft had already moved on, already turned toward the next encounter, the next mystery. And this is the nature of exploration, not to stay, but to pass through. To witness, to record, to send the knowledge back, and then to leave. Carrying the journey forward even as the place you've seen recedes behind you. Saturn remains. The rings remain, slowly raining into the planet, slowly dissolving. In 100 million years, they'll be gone. But for now, they catch the sunlight. They turn in silence. They hold their shape through mathematics and motion. And somewhere in the data, Voyager sent home, someone is still finding patterns. Still asking why this gap exists. Why this ringlet braids. Why beauty and chaos look so similar from far away. The spacecraft continued outward into colder regions, toward planets no human eye had ever seen up close, toward worlds so distant that sunlight arrives weak and pale, barely warmer than starlight, toward a planet that rolls instead of spins, a world knocked sideways by some ancient collision, its seasons measured in decades, its moons orbiting in a plane perpendicular to everything else in the solar system, toward Uranus, the tilted world where even the light seems confused about which way is up. Imagine waking up one day and discovering that everything you thought was up is now sideways. That's Uranus. The planet rotates at a 98-degree tilt, essentially lying on its side as it orbits the sun. During its 84 Earth-year journey around the solar system, each pole experiences 42 years of continuous sunlight, followed by 42 years of absolute darkness. Summer at the North Pole means the sun hangs almost directly overhead for 4 decades. Then comes an autumn that lasts 21 years. Then winter, a night that spans an entire human lifetime. When Voyager 2 arrived on January 24th, 1986, it became the first and still the only spacecraft to visit Uranus. The encounter lasted just 5.5 hours at closest approach, but in that brief window, Voyager transmitted images and data that remain our most detailed look at this strange, tilted world. What Voyager saw was a planet of profound quiet, almost eerily so. Uranus appears as a pale cyan sphere, featureless, smooth, like a marble made of frozen sky. The color comes from methane in the upper atmosphere. Methane absorbs red light and reflects blue and green. But unlike Jupiter's vivid bands or Saturn's subtle stripes, Uranus shows almost no structure, no storms visible from Voyager's distance, no swirling patterns, just a calm, cold blue. Scientists suggest this smoothness might be deceptive. The lack of visible features doesn't mean nothing is happening. It might mean that whatever happens occurs too deep to see beneath layers of methane haze that hide the dynamics below, a world that keeps its turbulence internal. How many of us have learned to do that, to appear smooth on the surface while everything underneath churns unseen? The planet is classified as an ice giant, not a gas giant like Jupiter or Saturn. The distinction matters. Uranus has a small rocky core, maybe 0. 5. Earth masses surrounded by a mantle of water, methane and ammonia. Ice is not ice in the solid sense, but superionic ice. A strange phase of matter where water molecules break apart under extreme pressure, allowing hydrogen ions to flow freely, while oxygen remains locked in a crystal lattice. It's ice that conducts electricity like metal. Ice that exists at temperatures over 2,000 degrees Celsius. The universe creates substances Earth never taught us to imagine. Above this mantle sits an atmosphere of hydrogen and helium, accounting for only about 15% of the planet's mass. Winds blow here, though Voyager couldn't measure their speed. In 1986, the planet looked too uniform. Later observations from the Hubble Space Telescope and ground-based instruments detected clouds measured wind speeds up to 900 kilometers per hour. But those discoveries came years after Voyager passed. At the time, Uranus seemed dormant, silent, a planet that had given up on drama. The axial tilt, 98 degrees, is Uranus's defining strangeness. Most planets spin like tops, their rotational axes roughly perpendicular to their orbital planes. Earth tilts 23.5 degrees, which gives us seasons. Mars tilts 25 degrees. Jupiter and Saturn barely tilt at all 3 degrees and 27 degrees respectively. But Uranus rolls. Its equator runs nearly vertical relative to its orbit. The poles take turns facing the sun directly. Scientists believe this tilt resulted from a massive collision early in the solar system's history, perhaps multiple collisions. Something roughly Earth-sized or larger slammed into Uranus, knocking it sideways. The impact was catastrophic, but not destructive. The planet survived, its gravity held, but its orientation changed forever. Trauma written in geometry. What's remarkable is that Uranus's moons orbit in the same tilted plane. Their orbits follow the planet's equator, perpendicular to the ecliptic. Either they formed after the collision condensing from the debris, or they were somehow swept into the new orientation. Voyager discovered 10 new moons at Uranus, adding to the 5 previously known from Earth-based observations. The major moons, Miranda, Ariel, Umbriel, Titania, Oberon, are all named after characters from Shakespeare and Alexander Pope, a literary tradition that continues for all Uranian satellites. Miranda is perhaps the strangest. A small moon only 471 kilometers in diameter, yet its surface looks like it's been taken apart and reassembled incorrectly. Voyager's images show regions of different terrain, jammed against each other, cratered highlands next to grooved lowlands, cliffs 20 kilometers high. One of them, Verona Rupes, is the tallest known cliff in the solar system. Scientists suggest Miranda might have been shattered by an impact and then reaccreted gravity, pulling the fragments back together into a jumbled whole. Or perhaps internal heating caused different regions to melt and resurface at different times, creating a patchwork geology. A world that broke and healed wrong. There's something deeply relatable about that. The way trauma rearranges us, the way we put ourselves back together, but the pieces don't quite fit the way they used to. Ariel shows signs of past geological activity, valleys, faults, smooth plains that suggest cryovolcanism. Not lava, but water or ammonia. Water mixtures erupting from the interior, freezing on the surface. Umbriel is dark, heavily cratered ancient. Titania has fault canyons hundreds of kilometers long, evidence of internal expansion or contraction. Oberon is scarred by large impacts at surface, old and cold. Each moon is a frozen record of violence and time. Voyager also discovered Uranus's rings, 11 of them narrow and dark, made of dust and small particles. They are faint compared to Saturn's rings, barely visible even in Voyager's images. The particles are charcoal dark, reflecting only 2% of the light that hits them. Scientists believe the rings are young, perhaps only 600 million years old, formed from shattered moons or captured material. The rings orbit in the planet's equatorial plane, which means from our perspective on Earth, we sometimes see them edge on, sometimes face on, depending on where Uranus is in its 84-year orbit. Between 2007 and 2009, Earth passed through the ring plane, and the rings briefly became nearly invisible, a disappearing act that happens twice each Uranian year. Even structures can vanish if you catch them at the wrong angle. The magnetosphere of Uranus surprised everyone. Unlike Earth's, which is roughly aligned with the planet's rotational axis, Uranus's magnetic field is tilted 59 degrees from its rotation axis and offset from the planet's center by about 1/3 of the radius. This creates a lopsided, wobbling magnetosphere. As the planet rotates every 24 hours, the magnetic field tumbles like a poorly thrown football. The magnetic poles sweep across the sky. Charged particles in the magnetosphere experience wildly varying conditions, depending on where they are in the rotation cycle. Scientists still don't fully understand why this misalignment exists. It might relate to the depth at which the magnetic field is generated, not from the core, but from the superionic ice mantle where pressure and temperature allow electrical conduction. A planet that can't align its insides with its outsides. The temperature at Uranus is cold in a way that's hard to imagine. The cloud tops hover around -224 degrees Celsius. At that temperature, methane condenses into ice crystals. Ammonia would be solid. Even carbon dioxide would freeze. But here's what's puzzling. Uranus emits very little heat. Planets typically radiate more energy than they receive from the sun, leftover heat from their formation, or heat generated by radioactive decay or gravitational contraction. Jupiter emits 1.7 times as much energy as it absorbs. Saturn emits 1.8 times. Neptune emits 2.6 times. Uranus emits 1.06 times. Almost nothing. It's nearly in perfect thermal equilibrium with sunlight. This suggests that Uranus has lost most of its internal heat, or that its internal heat is trapped beneath layers that insulate it from radiating into space. Either way, the planet is thermally unusual, colder than it should be given its mass and age, a world that's locked its warmth away. Voyager flew by during Uranian summer in the southern hemisphere. The South Pole pointed almost directly at the sun. The northern hemisphere was deep in its 42-year night. The spacecraft's instruments measured temperature, magnetic field, strength radio emissions, atmospheric composition. One discovery stood out. Uranus has an electroglow, a layer in the upper atmosphere where ultraviolet light from the sun excites hydrogen molecules, causing them to emit a faint glow. It's similar to Earth's air glow, that subtle luminescence visible from space at the edge of our atmosphere. Even in the cold, even tilted sideways, even locked in decades-long seasons, the planet glows. Faintly, but it glows. The encounter was brief. Voyager 2 was moving fast, over 13 kilometers per second relative to Uranus. It took images, made measurements, then accelerated onward using Uranus's gravity to redirect toward Neptune. There was no second chance, no follow-up mission. To this day, no other spacecraft has visited Uranus. Everything we know about this planet up close comes from those 5.5 hours in January 1986. Think about that. An entire world reduced to a single flyby. A handful of hours to observe, to record, to understand. And then it was over, and the spacecraft was gone, moving toward the next target, carrying its data home across billions of kilometers. In those hours, Voyager saw enough to rewrite the textbooks, discovered moons, measured the magnetosphere, mapped the rings, analyzed the atmosphere. But it also left questions. Why the extreme tilt? Why the thermal coldness? What drives the weather systems we can barely detect? What lies beneath the smooth cyan clouds? These questions remain. 40 years later, scientists still propose missions to Uranus, though none have been funded. The planet is too far, too cold, too difficult to reach. A full mission would require years of travel, a massive rocket-advanced technology to survive the environment. So, Uranus waits, rotating on its side, its poles taking turns facing the sun, its moons orbiting in their perpendicular plane, its magnetic field tumbling every 17 hours. A planet that lives differently, that refuses the standard orientation. That took a hit so severe it should have destroyed it, but instead just changed the way it spins, and maybe there's dignity in that. In surviving the catastrophic and continuing anyway, even if you're never quite the same. Even if your seasons are wrong, your axis tilted, your north and south confused. You still orbit, you still hold your moons, you still reflect the light that reaches you. Voyager's cameras captured one final image as the spacecraft departed Uranus, and its rings in a crescent backlit by the sun. A farewell shot showing the planet as a thin arc of light against the darkness. Then Voyager turned its instruments forward toward the last planet on its tour, toward Neptune, the final ice giant, another 1.8 billion kilometers ahead, toward winds faster than anything in the solar system, toward a moon orbiting backward, toward mysteries that would take 3 more years to reach. But that distance was nothing now. Voyager had already come so far. The spacecraft's plutonium heart still beat. The instruments still worked. The mission continued. And in the cold silence between Uranus and Neptune, in that empty space where sunlight arrives weak as starlight, Voyager drifted on, alone but purposeful, carrying its golden record, carrying the hopes of a species that built it and sent it farther than they could follow into the deep blue darkness where the ice giants sleep, toward the last world with a name, the last encounter, the final planetary goodbye before the infinite journey into interstellar space would truly begin. There's a storm on Neptune that appeared raged for 5 years, then vanished without explanation. No one knows where it went. When Voyager 2 reached Neptune on August 25, 1989, 12 years after launch, having traveled 4.4 billion kilometers, it found a world of impossible blue. Not the pale cyan of Uranus, but a deep, vivid azure that seemed too saturated to be real. The color comes from methane absorbing red light. Yes, but there's something else too. Something scientists still debate, trace amounts of an unknown compound that shifts the blue deeper, richer. A color we can see, but can't fully explain. Neptune is the last planet, the 8th and final world orbiting our sun. Beyond it lies only the Kuiper Belt, a realm of ice and rock and dwarf planets, cold bodies tumbling in the outer dark. Neptune marks the boundary between the solar system we know and the frontier we're still mapping. It's fitting somehow that the last planet is the one we understand least. Voyager's cameras captured Neptune in exquisite detail during the brief flyby, just under 5 hours at closest approach. The planet appeared alive, dynamic, streaked with bright cirrus clouds of methane ice crystals racing across the deep blue atmosphere, white streaks high and fast casting shadows on the cloud deck below, shadows visible from 4.8 billion kilometers away. This was nothing like Uranus's featureless calm. Neptune churns. The most prominent feature Voyager saw was the Great Dark Spot, an anticyclonic storm system, roughly the size of Earth, located at 22 degrees south latitude. It rotated counterclockwise, completing one revolution every 18.3 hours, faster than the planet's own 16-hour rotation period. The storm drifted westward relative to Neptune's surface, a wandering eye in the deep blue face. Around the dark spot's edges, bright white clouds formed companion clouds. Scientists called them made of methane ice condensing as gas rose from warmer depths. Below cooled and froze. The clouds changed shape hour by hour, torn by winds exceeding 2,100 kilometers per hour, the fastest winds ever measured in the solar system. For comparison, the strongest hurricane winds on Earth reach maybe 300 kilometers per hour. Neptune's winds are 7 times faster. But here's the mystery: when the Hubble Space Telescope looked at Neptune in 1994, just 5 years after Voyager's flyby, the great dark spot was gone, completely vanished, no trace, no remnant. The atmosphere had erased it. In its place, a new storm had formed in the northern hemisphere. Then that storm disappeared too. Then another appeared in the south. Neptune storms come and go, materializing and dissolving on time scales of years. They're not permanent features like Jupiter's Great Red Spot. They're temporary, ephemeral. They rage with unimaginable violence and then fade as if they never existed. How does a storm the size of Earth simply vanish? Scientists suggest Neptune's storms might be convective. Plumes, columns of warm gas rising from deep in the atmosphere, breaking through upper cloud layers, creating vortices that spin in the shearing winds. When the heat source weakens or shifts, the storm collapses, the vortex dissipates, the clouds scatter. But the exact mechanism remains unclear. Neptune is too far for detailed long-term observation. We get glimpses Voyagers fly by Hubble images every few years, ground-based telescope data when atmospheric conditions allow. Between these glimpses, the planet changes and we miss the transitions. We see the storm, we see the absence, we don't see the dying. Neptune emits 2.6 times more energy than it receives from the sun. That internal heat drives the weather powers. The wind sustains the storms. But where does the heat come from? The planet formed 4.5 billion years ago. It should have cooled by now, radiated away most of its primordial warmth. One theory involves differentiation, heavier materials sinking toward the core, releasing gravitational potential energy as heat. Another suggests that methane might condense in the upper atmosphere and rain down as diamonds, releasing heat as it falls and eventually melts under pressure deeper down. Diamond rain. It's a poetic idea, and the physics supports it. Laboratory experiments have shown that at the pressures and temperatures found in Neptune's mantle, methane can decompose carbon atoms, bond together, and diamonds crystallize from the surrounding fluid. A storm of gemstones falling through hydrogen and helium, burning with friction as they descend into the dark. The universe creates beauty in places no eye will ever see. Voyager discovered 6 new moons at Neptune, adding to the 2 previously known Triton and Nereid. The new moons are small, irregularly shaped, orbiting close to the planet. Naiad, Thalassa, Despina, Galatea, Larissa, Proteus, names from Greek and Roman water mythology, fitting for a planet named after the god of the sea. But Triton is the centerpiece. The largest moon, 706 kilometers in diameter, smaller than Earth's moon, but larger than Pluto. And Triton is strange in a way that suggests violence. It orbits retrograde, backward, opposite to Neptune's rotation and opposite to the direction all the other moons orbit. This is dynamically unstable. A retrograde orbit can't last forever. Tidal forces are gradually slowing, Triton pulling it closer to Neptune. In perhaps 3.6 billion years, Triton will cross Neptune's Roche, limit the boundary where tidal forces overcome gravity, and the moon will shatter, torn apart, its fragments forming a ring system that might rival Saturn's. But for now, Triton survives, strange and cold and geologically active. Voyager's closest approach to Triton came within 40,000 kilometers. The images revealed a surface like nowhere else, pinkish mottled, streaked with dark lines dotted with smooth plains and ridged terrain. The colors come from irradiated methane ice, frozen methane exposed to cosmic rays and solar ultraviolet, slowly transforming into complex organic compounds called tholins. The surface temperature is minus 235 degrees Celsius, making Triton one of the coldest surfaces ever measured in the solar system. Nitrogen ice covers much of the terrain. Frozen methane deposits glisten in the faint sunlight. And yet, Triton is active. Voyager detected plumes, geysers of nitrogen gas erupting from beneath the surface, carrying dark particles up to 8 kilometers high, where stratospheric winds catch them and spread them downwind for up to 150 kilometers. These plumes leave dark streaks on the surface visible in Voyager's images, proof that Triton's interior retains enough heat to drive cryovolcanism. But how Triton is tiny, it should be geologically dead, frozen, solid, inert. Yet something heats it. Scientists believe the retrograde orbit is key tidal heating from Neptune flexes. Triton's interior generating friction, melting the subsurface ices just enough to allow eruptions. The same force that will eventually destroy Triton is what keeps it alive now. There's a parallel worth considering. How often does the thing that sustains us also carry the seeds of our ending? Triton's retrograde orbit also suggests it wasn't born where it is. Moons form from the same rotating disk that forms their planet they inherit. The disk's direction, orbit prograde naturally. A retrograde moon must have been captured. Scientists believe Triton originated in the Kuiper Belt, a large icy body similar to Pluto orbiting the Sun independently. At some point, perhaps 3 to 4 billion years ago, Triton wandered too close to Neptune. The planet's gravity captured it, pulled it into orbit, but the capture was violent. Triton's original orbit was probably highly elliptical. Tidal forces gradually circularized it over millions of years. But that process generated enormous heat enough to melt Triton's interior, erase its original surface, reset its geology entirely. The moon we see now is not the body that was captured. It's what remains after the trauma. Nereid, Neptune's other major moon, has the most eccentric orbit of any moon in the solar system. Its distance from Neptune varies from 1.4 million to 9.6 million kilometers over the course of one orbit. Scientists suggest Nereid might have been a regular moon-orbiting prograde and circular until Triton's capture disrupted the system. Triton's gravity threw everything into chaos, and Nereid's orbit was stretched into its current extreme ellipse. One arrival changed everything. Scatter the old order, left survivors in strange trajectories. Voyager also discovered Neptune's rings, 5 of them narrow and faint, made of dust. But the rings aren't uniform. The outermost ring Adams contains clumps dense arcs of material named Liberté, Égalité, Fraternité, and Courage. These arcs are dynamically puzzling. Material and planetary rings should spread out over time, smoothed by collisions and gravitational perturbations. Clumps shouldn't persist. Scientists suggest the small moon, Galatea, orbiting just inside the Adams ring, might shepherd the arcs its gravity, preventing them from dispersing. But the mechanism isn't fully understood. The arcs exist. They shouldn't. They do anyway. The universe frequently does things that shouldn't work, and they work anyway. Neptune's atmosphere shows structure that Uranus's lacks, distinct bands of latitude zones and belts like Jupiter's, but subtler. The planet rotates quickly once every 16. 11 hours and differential rotation creates shearing winds. The equator rotates slower than mid-latitudes, which rotates slower than the poles. This creates jet streams boundaries where winds flow in opposite directions. The storms form at these boundaries. They are vortices born from sheer spinning points where the atmosphere can't decide which direction to turn, so it turns both. Voyager measured wind speeds directly by tracking cloud features across multiple images. The results were shocking: 2100 kilometers per hour in the upper atmosphere. But here's what's even stranger: Neptune receives only 1/900th the sunlight Earth does. At that distance, the sun is barely brighter than a full moon appears from Earth. How does a planet with almost no solar energy drive the fastest winds in the solar system? The answer is that Neptune's weather isn't solar-powered. It's driven from below by internal heat. The planet is its own furnace, warming itself, creating convection, driving circulation independent of the sun. This has implications. It means Neptune's weather doesn't depend on external conditions. It's self-sustaining. The storms rage not because the sun heats them, but because the planet itself refuses to be cold and still. Voyager's instruments detected radio emissions from Neptune, bursts of static generated by lightning in the deep atmosphere, or by interactions between the planet's magnetic field and charged particles in the magnetosphere. These emissions follow patterns, frequencies, rhythms that scientists are still analyzing. The planet speaks. We're learning its language slowly. Neptune's magnetic field, like Uranus's, is tilted relative to the rotation axis 47 degrees offset compared to Uranus's 59 degrees. And like Uranus, the magnetic field is offset from the planet's center. This creates a complex asymmetric magnetosphere that tumbles as the planet rotates. Some scientists believe this commonality between Uranus and Neptune, tilted offset magnetic fields, suggests their fields are generated in the mantle rather than the core, in regions where supersonic water ice allows electrical conduction. If true, it means ice giants generate magnetism differently than rocky or gas giant planets. Different structures, different rules, different physics. The flyby ended quickly. Voyager 2 came in fast, took its measurements, captured its images, and accelerated away using Neptune's gravity for one final boost, not toward another planet, but toward interstellar space. The trajectory was set. The tour was complete. As Voyager departed, its cameras turned back one last time. Neptune appeared as a crescent, a thin arc of deep blue against the black. Triton hung nearby, a faint crescent too, its pinkish surface barely visible. Then Voyager shut off most of its instruments to conserve power. The cameras went dark. The mission's primary objectives were fulfilled. What came next was bonus, an extended mission into the unknown, a journey beyond any destination. But before we follow Voyager into that final darkness, there's one more image to see. One photograph that changed how humanity sees itself. A picture taken not of another world, but of our own from a distance so vast it reduced everything we've ever known to a fraction of a single pixel. A portrait of Earth from the edge of the solar system. A reminder of how small we are and how far we've sent our eyes to look back at ourselves. That image waits ahead. But first, the spacecraft had to travel billions of kilometers in the opposite direction, away from Neptune, away from the sun, climbing out of the solar system's gravitational well toward a place where even our star becomes just another point of light. Toward the photograph that would make Carl Sagan weep, toward the pale blue dot suspended in a beam of scattered sunlight. Toward the moment when Voyager would turn its camera homeward and show us what we look like from the place where we've never been. On February 14, 1990, Voyager 1 took a photograph from 6 billion kilometers away. In it, Earth is 0.12 pixels, a pale blue dot suspended in a beam of scattered sunlight. No continents visible, no oceans, no clouds. Just a point of light so small you could miss it if you didn't know where to look. Carl Sagan requested that photograph. He convinced NASA to turn Voyager's camera back toward Earth one final time before the imaging system was shut down forever to conserve power. The camera had been off for years. There was nothing scientifically valuable to photograph in empty space. But Sagan wanted the portrait anyway. Not for science, for perspective. The image arrived at Earth as radio data ones and zeros transmitted across the solar system at the speed of light, taking 5.5 hours to reach the antennas. Engineers reconstructed the pixels, and there it was, home smaller than the smallest grain of sand held at arm's length. When Sagan saw the photograph, he wrote words that still echo, "Look again at that dot. That's here, that's home, that's us." He continued describing how everyone we've ever heard of lived their lives on that mote of dust. Every saint and sinner, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, every hopeful child, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on that dot, a single pixel containing all of human history. The photograph is part of a larger collection called the Family Portrait 60 Images, taken over the course of several hours as Voyager systematically pointed its camera at the sun and the planets. The goal was to capture as much of the solar system as possible in a single mosaic. Mercury was too close to the sun's glare to photograph. Mars was too faint at that distance. Pluto, small and distant, was lost in the background stars. But Venus, Earth, Jupiter, Saturn, Uranus, and Neptune all appeared points of light scattered across the darkness, proof that we orbit a star among billions. But it's Earth's image that endures, the pale blue dot. Not because it's scientifically unique, but because of what it represents. From Voyager's perspective, Earth sat inside a band of scattered sunlight, a lens flare artifact, created by light diffracting through the camera's optics. The engineers knew this would happen. They had warned Sagan the image quality would be compromised, but Sagan insisted. He wanted Earth photographed precisely because it would be so small, so insignificant, so easily lost in the cosmic background. He wanted us to see ourselves the way the universe sees us. The photograph is humbling in a way that words struggle to convey. When you look at it, really look at it, something shifts internally. The scale of your concerns recalibrates. The arguments you had yesterday, the grievances you've carried, the pride you've held, they don't disappear, but they soften. They become contextual, conditional. On that dot, every battle was fought, every border drawn, every ideology defended, every war waged over territory that amounts to a fraction of a pixel. Think about the empires that rose and fell on that dot. The Mongol Empire at its height controlled roughly 24 million square kilometers, about 16% of Earth's land surface. From Voyager's distance, that empire occupies less than 0.02 pixels. The Roman Empire, the British Empire, every kingdom and nation-state that ever existed, all contained within a speck of light. From 6 billion kilometers, the borders are invisible, the nations indistinguishable, the wars incomprehensible. Sagan's reflection on the photograph includes a line that cuts deeper each time you hear it. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph, they could become the momentary masters of a fraction of a dot. A fraction of a dot. Does that change how you think about power, about conquest, about the things we're willing to destroy for the sake of control? The pale blue dot image arrived at a specific cultural moment. The Cold War was ending. The Berlin Wall had fallen just months earlier. The Soviet Union was unraveling. Humanity was beginning to see itself as a single species rather than divided factions. The photograph reinforced that shift. It offered visual proof of our unity, not political unity, not ideological unity, but physical unity. We share one small world, one atmosphere, one biosphere. The divisions we create are real to us, but invisible from any meaningful distance. Environmental advocates embrace the image. Here was Earth finite and fragile, floating in an immensity that doesn't care whether we survive. No help is coming from the void. No rescue mission will arrive if we ruin the only habitable world we know. The photograph became an icon of the environmental movement, reproduced on posters, book covers, classroom walls. It appears in documentaries, philosophy lectures, existential meditations. It's been viewed by hundreds of millions of people. But here's what's easy to miss. The photograph almost didn't happen. Sagan had been requesting it for years. He first suggested the idea in 1981, shortly after Voyager 1's encounter with Saturn. NASA resisted. There was no scientific justification. The camera was needed for other observations. Turning it back toward the inner solar system risked pointing it too close to the sun, potentially damaging the optics. Sagan persisted. He argued the value wasn't scientific, but philosophical. The image would provide perspective, a sense of context for humanity's place in the cosmos. NASA remained skeptical. Spacecraft time is precious. Every command, every maneuver, every photograph must justify its cost in energy and data transmission. It took nearly a decade, but eventually Sagan convinced Candy Hansen, a Voyager imaging team member, who convinced others, who convinced mission planners, who finally approved a narrow window, February 14, 1990, when Voyager 1 would be far enough from Neptune to safely point its camera sunward without interference. The window was small, the spacecraft's tape recorder had limited capacity. Only 60 images could be captured. The camera would then be shut down permanently. Sagan got his photograph because he refused to stop asking. How often do we assume the answer is no before we even make the request? The technical details of the image are worth understanding. Voyager 1 was 54 billion kilometers from Earth when the photograph was taken. At that distance, Earth subtends an angle of just 0.12 pixels in the camera's field of view. The actual size of Earth is 12^42 kilometers in diameter, but from Voyager's perspective, it's smaller than the resolution of the imaging system. The camera's narrow angle lens had a field of view of 0.424 degrees. The image was taken through a blue filter, which is why Earth appears bluish rather than the more accurate pale blue-white. The sunlight streak across the image is an optical artifact, diffracted light scattering through the camera's internal structure. Engineers could have chosen a different filter, a different angle, a different timing to minimize the glare. But maybe the glare is part of the meaning. Earth caught in a beam of light from the sun, it orbits. A tiny world illuminated by the star that gives it life, fragile, temporary, held in place by gravity and nothing else. Sagan's full reflection on the photograph, later published in his book, Pale Blue Dot, includes lines that feel almost unbearably poignant. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity and all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. Read that again. No hint that help will come from elsewhere to save us from ourselves. It's not a hopeless statement. It's a clarifying one. We are the stewards of our own survival. The universe is vast, indifferent, magnificent, but it will not intervene. If we ruin this pale blue dot, there's no backup planet waiting nearby, no rescue fleet, no cosmic parent to fix our mistakes. The photograph makes that truth visible. Some people find this perspective depressing. If we're so small, so insignificant, what's the point? Why try? Why care? But others, and Sagan was among them, find it liberating. Yes, we're small. Yes, the universe is indifferent. But that smallness doesn't diminish meaning. It clarifies it. The meaning isn't imposed from outside. It's created here on this dot by us through how we treat each other and the world we share. Sagan's final lines on the pale blue dot might be the most important. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. To deal more kindly with one another. Not because some cosmic authority demands it, not because we'll be rewarded or punished, but because we're here together on this speck, and kindness is the only rational response to our shared fragility. The photograph has been analyzed, discussed, written about for decades. Philosophers use it as a starting point for conversations about meaning and scale. Therapists reference it when helping people contextualize anxiety. Educators show it to students to illustrate perspective taking. But the image itself remains simple, a point of light, a pixel, less than a pixel. And somehow, that simplicity is exactly what makes it powerful. When astronauts see Earth from space, from the International Station, from the Moon, they report a cognitive shift called the overview effect. Borders vanish. National identities soften. The planet appears as a unified whole, a single organism, fragile and beautiful. Astronauts come back changed, describing an overwhelming sense of interconnectedness and a desire to protect the planet. The pale blue dot offers a version of that experience from even farther away. Not from low Earth orbit, but from the edge of the solar system. From a distance where Earth is no longer a sphere, but a point. Where the overview effect becomes the ultimate perspective. Voyager's camera was shut down shortly after the family portrait was completed. The spacecraft no longer had a use for it. The mission was shifting from planetary exploration to interstellar journey. What mattered now was measuring the boundary of the sun's influence, detecting cosmic rays, mapping magnetic fields. But before the camera went dark, it gave us that image, that single pixel, that reminder. And maybe that's enough. Maybe one photograph taken from the edge of everything we've touched, showing us how small and how precious we are, maybe that's worth the entire mission. The pale blue dot doesn't answer questions, it asks them. What are we doing with this fragile world? How are we treating the only home we've ever known? What kind of ancestors will we be to those who come after? And perhaps most urgently, can we see past our divisions, long enough to recognize that we're all standing on the same small dot, held together by nothing but gravity and luck. Voyager continued outward after the photograph was taken. The camera stayed off. The spacecraft moved into regions where sunlight grows faint and cold, where the solar wind weakens, where the boundary between the sun's domain and the interstellar medium begins to blur. That boundary has a name, the heliopause, and Voyager was heading straight toward it, carrying its golden record, carrying its silent cameras, carrying the memory of every world it had seen and every image it had sent home, including one image that showed us ourselves small and blue and alone, suspended in the great dark. A reminder that we're all passengers on this pale blue dot, and the journey we share is all we have. There's a place where the sun's wind stops blowing, a boundary where everything that makes our solar system feel like home fades into something else, something older, something that was here before the sun ignited and will remain long after it dies. On August 25, 2012, exactly 35 years after launch, Voyager 1 crossed that boundary. It left the heliosphere, the bubble of solar wind and magnetic field that surrounds our sun and planets, and entered interstellar space, the first human-made object to do so. Voyager 2 followed on November 5, 2018, crossing at a different location, providing scientists with 2 data points to compare. 2 exits from the same room, showing that the walls aren't quite where we thought they were. The crossing wasn't dramatic. No alarm sounded, no sudden jolt. The spacecraft didn't feel anything. It has no capacity for sensation. It just moved from one medium into another, from plasma dominated by the sun to plasma dominated by the galaxy. But the instruments noticed. The data changed. And back on Earth, scientists realize we've left home. The heliosphere is vast. It extends roughly 123 astronomical units from the sun in the direction Voyager 1 traveled 1 astronomical unit, being the distance from Earth to the sun about 150 million kilometers. So, 123 AU is approximately 18 billion kilometers. The bubble isn't perfectly spherical. It stretched in the direction of the sun's motion, through the galaxy compressed where interstellar wind pushes back. Think of it as a teardrop shape with the sun near the rounded end and a long tail streaming behind. For decades, scientists theorized about this boundary but had no direct measurements. Models predicted where it should be, but models are only as good as their assumptions. Voyager would provide ground truth, or rather space truth. The journey toward the heliopause took decades. After Neptune Voyager 1 climbed northward out of the ecliptic plane, the flat disk where planets orbit, it moved into emptier regions where asteroids thin out, where even the Kuiper Belt objects are sparse and scattered. The spacecraft traveled through what seems from Earth like absolute void. But space is never truly empty. There's always something: hydrogen atoms, dust grains, magnetic fields, cosmic rays. The density is unimaginably low, 1 atom per cubic centimeter in some regions. Compare that to Earth's atmosphere at sea level, 1019 molecules per cubic centimeter. But that 1 atom per cubic centimeter adds up over billions of kilometers. It creates pressure. It interacts with the solar wind. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the sun at speeds of 400 to 750 kilometers per second. The sun sheds about 1 million tons of material per second through this wind. It's been doing this for 4.6 billion years. Somehow the sun hasn't run out. This wind carries the sun's magnetic field, with it stretching it into a spiral shape called the Parker spiral, named after physicist Eugene Parker, who predicted the solar wind's existence in 1958. For decades, his theory was controversial. Many scientists didn't believe the sun continuously ejected plasma, but spacecraft measurements prove Parker correct. He lived to see Voyager confirm his predictions at the edge of the solar system. Parker died in 2022, knowing his work had been validated across billions of kilometers. The solar wind flows outward until it meets the interstellar medium gas and dust between the star's remnants of ancient supernovae material slowly collapsing into future stars. The interstellar medium doesn't flow from any one source. It's ambient distributed, moving with the galaxy's rotation and local currents. When the solar wind meets the interstellar medium, it slows down. The boundary where this happens is called the termination shock. Voyager 1 crossed it on December 16, 2004, at a distance of 94 AU. The spacecraft's instruments detected a sudden drop in solar wind speed, an increase in temperature, a rise in magnetic field strength. The solar wind encountering resistance compressed and heated like air compressing in front of a supersonic jet. Shock waves formed. Turbulence increased. Voyager was entering the heliosheath, the region between the termination shock and the heliopause where solar wind slows but hasn't stopped. For 8 more years, Voyager 1 traveled through the heliosheath. The instruments measured fluctuating magnetic fields, varying particle densities, unexpected structures. The data didn't always match the models. The heliosheath was messier than predicted layered turbulent dynamic. Scientists debate the exact moment Voyager 1 crossed the heliopause. The spacecraft doesn't carry a plasma detector. It failed years earlier, so it couldn't directly measure the solar wind stopping. Instead, scientists inferred the crossing from other data: the sudden increase in galactic cosmic rays, the disappearance of lower energy solar particles, changes in magnetic field direction. The date most widely accepted is August 25, 2012, but some data suggested earlier crossings or multiple crossings as the boundary moved. The heliopause isn't static. It breathes. It shifts inward and outward depending on solar activity, interstellar pressure, magnetic field dynamics. Voyager might have crossed it, then recrossed as the boundary moved, then crossed again, definitively. Or it crossed once and the data simply took time to clarify. The uncertainty doesn't diminish the achievement. We left. We measured. We're still out there. When Voyager 2 crossed in 2018, it carried a working plasma detector. It directly measured the solar wind dropping to 0. confirming what instruments inferred from Voyager 1's crossing. The two spacecraft crossed at different distances. Voyager 1 at 122 AU, Voyager 2 at 119 AU, proving the heliopause isn't a perfect sphere. The shape changes, the boundary warps. Space, even in its emptiness, has topology. Beyond the heliopause, the environment changes profoundly. Galactic cosmic rays, high-energy particles accelerated by supernovae and other violent events across the galaxy flood in. Within the heliosphere, the sun's magnetic field partially shields us from these rays. Outside, there's no shield. Voyager's instruments detected cosmic ray levels 4 times higher than inside the heliosphere. These are the same cosmic rays that pose radiation hazards to astronauts. The same particles that strike Earth's atmosphere, creating cascades of secondary particles, some of which reach the surface and pass through our bodies every second. We live inside a protective bubble. Voyager left that bubble and survived. The magnetic field orientation also changed. Inside the heliosphere, the magnetic field is dragged outward by the solar wind, creating the Parker spiral. Outside the field aligns with the interstellar medium, shaped by the galaxy's magnetic structure, by currents flowing between stars. Voyager measured this transition. The field direction shifted, stabilized, stopped fluctuating with solar activity. The spacecraft was feeling the galaxy's pulse instead of the sun's. Interstellar space isn't silent in the way we imagine silence. It's filled with plasma waves, oscillations in the charged gas propagating like ripples on a pond. Voyager's instruments detect these waves as radio emissions, frequencies between a few hundred hertz and several kilohertz. Scientists converted these signals into audio files, letting us hear what interstellar space sounds like. It's eerie, a steady hum punctuated by rising and falling tones, static bursts, low-frequency drones. Not music, not speech. Just the universe's ambient noise frequencies created by plasma vibrating in magnetic fields. Voyager hears this constantly now. The sound of the space between stars. Does that change how you imagine emptiness? That even the void hums? The spacecraft's power supply continues to fade. The plutonium-238 in the radioisotope thermoelectric generators decays with a half-life of 87.7 years. The generators produce less wattage each year, about 4 watts less annually. Engineers have been shutting down non-essential systems to conserve power, prioritizing instruments that measure the interstellar medium. The heaters for some instruments were turned off years ago. Those instruments now operate far below their design temperatures, in conditions the engineers never tested. And yet, they still function, still send data, still report what they're measuring in the cold and dark. Voyager 1 currently produces about 249 watts. Voyager 2 produces slightly more, around 255 watts. For comparison, a standard incandescent light bulb uses 60 watts. The spacecraft that left the solar system runs on less power than 4 light bulbs. At current decay rates, the spacecraft will fall below the minimum power threshold to operate any instruments around 2025 to 2030. One by one, the instruments will shut down. First the ultraviolet spectrometer, then the magnetometer, then the cosmic ray detector. Finally, the plasma wave instrument, the last voice listening to the hum of interstellar space. And then silence. Not because the spacecraft stopped moving, but because we can no longer hear it. The radio signal from Voyager 1 is currently about 23 watts weaker than a refrigerator light bulb, and it takes over 22 hours to reach Earth, traveling at the speed of light. By the time the signal arrives, it's been diluted across 18 billion kilometers, spread so thin that NASA's Deep Space Network antennas need 70-meter dishes to detect it. The signal is roughly 20 billion times weaker than the power needed to operate a digital wristwatch. And yet, we still hear it, still decode the data, still receive measurements from the edge of everything we've touched. How much effort does it take to stay connected across that distance? Not the spacecraft's effort, it just transmits. Our effort. Building antennas, maintaining the deep space network, funding the mission decades after the headlines faded, training engineers to work with 1970s technology, preserving the knowledge of how to communicate with something so far away. Voyager's longevity isn't just engineering, it's commitment. When the last instrument shuts down, Voyager will continue coasting. Its trajectory is set. In about 300 years, Voyager 1 will reach the inner edge of the Oort cloud, a spherical shell of icy bodies surrounding the solar system at distances from 2,000 to 100,000 AU. It will spend roughly 30,000 years passing through the Oort cloud. Then it will exit into true interstellar space, the space between star systems, where the sun is just another point of light and the nearest stars are years away even at light speed. In about 40,000 years, Voyager 1 will pass within 1.6 light years of the star Gliese 445 in the constellation Camelopardalis. It won't be captured, it won't slow down. It will drift past silent and dark, carrying its golden record. By then, humanity will be unrecognizably different or gone. The spacecraft will remain a time capsule from a species that built machines and sent them farther than they could follow. The heliopause crossing marked a transition from the sun's domain to the galaxy's. But it wasn't an ending, it was a threshold. The mission continues even as power fades, even as systems fail, even as the distance grows too vast for real-time conversation. Voyager still speaks. We still listen. And in that exchange across billions of kilometers and decades of time, there's something that feels like hope. Not hope for rescue or reward, but hope that the act of reaching outward matters. That the attempt to understand, to measure, to witness, that this carries its own justification. We are a species that builds machines and sends them into the dark. Not because we expect them to return, but because we need to know what's out there. Because curiosity in the end is stronger than fear. Voyager crossed into interstellar space and found it wasn't empty. It hums, it vibrates, it flows with currents older than our sun. The galaxy breathes and Voyager is learning its rhythm. But the crossing also clarified something else, a truth that's been unfolding since the spacecraft left Earth in 1977. That leaving is easier than staying connected. That distance doesn't end a relationship, but it transforms it. That we can speak into the void and trust the words will travel even if we never hear them arrive. And somewhere ahead, farther than Voyager has yet traveled, lies the next boundary, the next transition, the place where even the galaxy's influence fades and the true depth of intergalactic space begins. Voyager won't reach it. But the fact that we sent something that far, that we built machines capable of crossing thresholds we can barely imagine, means we've already touched what lies beyond. We've tasted infinity, and we're still hungry. The spacecraft drifts onward, its golden record spinning silently, its cameras dark, its instruments measuring the spaces between everything. And back on Earth, we wait for the signal. We point our antennas toward the coordinates where we know Voyager should be. We listen for the faint whisper of data, the proof that it's still out there, still moving, still carrying us forward into the dark, still speaking, still reaching, still refusing to let distance mean goodbye. There's a phonograph record made of gold-plated copper spinning through interstellar space right now. It contains the sound of a kiss, a heartbeat, a baby crying, Chuck Berry playing guitar, whale songs, wind and rain and thunder, the word hello in 55 languages, brainwaves of a woman thinking about love, and instructions on how to play it etched onto the cover, assuming whoever finds it understands physics geometry and the concept of recorded sound. The golden record wasn't part of Voyager's original mission design. It was added later almost as an afterthought, though afterthought doesn't capture the urgency and care with which it was assembled. Carl Sagan led the project working with a small team, including Anne Druyan, Timothy Ferris, Linda Salzman Sagan, and artist John Lomberg. They had 6 weeks. 6 weeks to decide what sounds and images would represent all of human civilization. 6 weeks to condense 4.5 billion years of Earth's history and 200,000 years of human culture into 90 minutes of audio and 116 images. How do you choose what to include when you're speaking for everyone who's ever lived? The team started with fundamental questions. What is Earth? What is life? What are humans? They decided to begin with sounds of the planet itself. Wind, rain, surf, thunder, mud, pots, earthquakes, volcanoes, the sounds of a geologically active world. Then the sounds of life crickets, frogs, birds, hyenas, elephants, chimpanzees, dogs, footsteps, heartbeats, laughter. A sequence that moves from simple organisms to complex social mammals to humans. A sonic evolutionary tree. The musical selections were perhaps the most contested. How do you represent human music when every culture has traditions spanning millennia? The team chose 27 pieces trying to balance geographical diversity, historical depth, and emotional range. Bach appears twice, once with the Brandenburg Concerto No. 2, once with the Prelude and Fugue in C from the Well-Tempered Clavier, performed by Glenn Gould. Some argued Bach was overrepresented. Others joked the real problem was they didn't send more Bach. Music that feels mathematically inevitable, as if it existed before humans discovered it. Beethoven's Fifth Symphony is there, the opening movement recognizable to billions. Stravinsky's Rite of Spring, angular and modern, depicting pagan ritual and sacrifice. Mozart's Queen of the Night aria from the Magic Flute. A soprano voice hitting impossibly high notes, proof of what human vocal cords can achieve with training. But also, a Navajo night chant, a Peruvian panpipe piece, Georgian choral singing, a Javanese gamelan orchestra, Bulgarian folk music featuring Valja Balkanska's voice, which sounds ancient even though it was recorded in 1968. Australian Aboriginal songs. Music from Zaire, Senegal, China, India, Japan, Mexico. And Chuck Berry's Johnny B. Good, rock and roll, electric guitar. A song about a poor boy who could play guitar like ringing a bell, who might someday have his name in lights. When Barry heard his song was going to the stars, he reportedly said, "Well, I sure hope they enjoy it." The spoken greetings are brief, 55 languages, 55 people saying hello in their own way. The ancient Greek greeting translates to, "Greetings to you whoever you are. We come in friendship to those who are friends." The Sumerian greeting in a language dead for over 2 millennia offers welcome. The Mandarin greeting is spoken by the project's young daughter. "Hope everyone's well. We are thinking about you all. Please come here to visit when you have time." An invitation issued to the cosmos. The English greeting spoken by Nick Sagan. Carl Sagan's 6-year-old son says simply, "Hello from the children of planet Earth." His voice is small, uncertain, slightly shy. It's the voice of a child who doesn't yet understand what he's speaking into. The recording captured him perfectly hopeful, tentative, trusting. That voice is now 15 billion miles from home, traveling at 38,000 miles per hour. By the time Nick Sagan is old enough to have great-great-grandchildren, his childhood voice will still be moving through the galaxy, still saying hello. Does that feel comforting or haunting, that our voices can outlive us by millions of years? The images include scientific diagrams, mathematical definitions, the structure of DNA, human anatomy, fertilization, and fetal development. There are images of Earth, deserts, oceans, forests, mountains, rivers, sunsets. Images of life, insects, fish, reptiles, birds, mammals. Images of humans, children, families, people eating people, working, people dancing. There's a supermarket, a traffic jam, a violinist, a page from Newton's Principia Mathematica, the Taj Mahal, the Great Wall of China, the Sydney Opera House, a string quartet playing, an Olympic sprinter mid-stride, And there's an X-ray of a human hand, Andruyan's hand, actually showing bones through flesh. A reminder that we're material beings built from calcium and carbon, same elements forged in dying stars. One image caused significant controversy. A silhouette of a nude man and woman, scientifically accurate, showing human anatomy without sexualization. NASA initially resisted including it. Some felt it was too explicit. Others argued that hiding our own bodies would be dishonest, Sagan insisted. If we're introducing ourselves to another intelligence, we should show what we actually look like. The image stayed, though. It's notably more modest than the nude figures on the earlier Pioneer plaques. We're comfortable sending our music into space, but anxious about showing our bodies. What does that say about us? The record also contains something unprecedented: brainwaves. Andruyan volunteered to have her brain activity recorded via EEG while she meditated, thinking through a structured sequence of ideas and emotions. She thought about the history of Earth, about evolution, about human civilization, its triumphs and failures, about love. She was newly in love with Carl Sagan at the time. They would marry shortly after the Voyager launch. Her meditation included thoughts of him, of their future together, of the overwhelming improbability and preciousness of consciousness. Those thoughts were encoded as audio pulses and frequencies representing neuronal activity. When played back, they sound abstract, almost musical, but encoded within them are the electrical patterns of a human mind contemplating existence. A recording of thinking itself. The cover of the golden record is electroplated with ultra-pure uranium-238, not for any symbolic reason but as a time marker. Uranium-238 decays into lead-206 with a half-life of 4.468 billion years. Any civilization that finds the record and understands nuclear physics could measure the ratio of uranium to lead and calculate how long the record has been traveling. It's a timestamp that will remain legible for billions of years. The instructions for playing the record are etched onto the aluminum cover. They use the hydrogen atom, the most common atom in the universe, as a reference for time and length. A diagram shows how to extract the stylus stored inside, how fast to spin the record, how to decode the analog waveforms into images and sound. The instructions assume the finder understands binary numbers, understands waveforms, understands the concept of recorded media. These are not small assumptions, but the team reasoned any civilization capable of intercepting a spacecraft would possess technology at least equal to ours. They would understand physics. They could decode the symbols given time and effort, or they couldn't, and the record would remain beautiful but unreadable, a golden disc covered in mysterious etchings, proof that someone tried to communicate but failed. The record was designed to last 1 billion years in the vacuum of space. No oxidation, no weathering, just cosmic rays and micrometeorite impacts. The grooves are etched deep enough to survive minor damage. The gold plating resists erosion. In 1 billion years, the sun will be 10% brighter. Earth's oceans might be boiling. Complex life might be extinct. But the golden record will still be intact, spinning through the dark, waiting. The project cost about $50,000, roughly $250,000 in today's dollars. For that price, humanity bought a message that will outlast everything we've ever built on Earth. Outlast the pyramids, outlast the Great Wall, outlast Mount Rushmore, which will erode completely in about 7.2 million years. The golden record will outlast human memory of its own creation. There are things the record doesn't include. No war sounds, no weapons, no images of violence or suffering. This was deliberate. Sagan and his team wanted to present humanity at its best, not denying our capacity for harm, but choosing to emphasize our capacity for beauty, curiosity, compassion. Some criticize this as dishonest. We're not always beautiful. We destroy as much as we create. Sending only our best self is a lie by omission. But others argued if you're introducing yourself to a stranger, you don't lead with your worst moments. You show what you aspire to be. The record isn't a documentary, it's a greeting, and greetings emphasize hope. Which version do you send? The honest one or the hopeful one? And are they really different? The record includes the sound of a mother kissing her child, a soft, wet sound, intimate and tender. It includes Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, a slide guitar piece so mournful it sounds like the earth itself weeping. It includes laughter, which needs no translation, and it includes one sound that almost got cut, the sound of a pulsar. A pulsar is a rotating neutron star, emitting beams of radiation like a cosmic lighthouse. As the beam sweeps past Earth, we detect regular pulses, hence the name. The record includes a pulsar map on its cover, showing the sun's position relative to 14 pulsars, allowing anyone who finds the record to triangulate where it came from. But the team also included the actual sound of a pulsar radio waves converted to audio. It sounds like a rapid ticking mechanical and alien, a natural object producing a rhythm so precise it seems artificial. When astronomers first detected pulsars in 1967, they briefly considered the possibility they were alien beacons. They called the first pulsar LGM-1, Little Green Men, 1. It wasn't aliens, it was physics. But the name captures the moment of wonder before understanding arrived. The golden record carries that wonder. Physics made audible, stars made sound. The record will not be found, not in any time frame that matters to us. The nearest star to Voyager 1's trajectory is Gliese, 445 1.6 light-years away, at closest approach around 40,000 years from now. Even if a civilization exists there, even if they have technology to detect and retrieve a small spacecraft, the odds of them noticing Voyager are astronomically small. Space is vast. Voyager is tiny. It's not transmitting anymore or won't be soon. It's not lit. It's just a dark object moving through darkness, nearly invisible against the cosmic background. The golden record will almost certainly never be played by anyone except humans on Earth, listening to the master copies stored in archives. But almost certainly isn't certainly. And that tiny probability, that infinitesimal chance that someone somewhere billions of years from now might find it, that chance justified the effort. Because the record wasn't really for aliens. It was for us. It was a mirror held up to humanity, asking if you had to explain yourselves to someone who knew nothing about you. What would you say? What sounds would you choose? What images? What music? The act of choosing revealed what we value. Music, language, laughter, science, nature, connection. We sent sounds of the earth because we love this planet even when we fail to protect it. We sent greetings in 55 languages because diversity is our strength even when we forget. We sent mathematics and diagrams because understanding the universe matters to us even when we don't always act like it. The record is a time capsule not for aliens but for ourselves. A snapshot of who we were in 1977, sent into the future, preserved against the entropy that erases everything else. When the last human has died, and Earth is a cold, dead rock orbiting a red giant sun, the golden record will still exist. Still playing our music to no one. Still saying hello in 55 languages to the silence. Still carrying the sound of a mother kissing her child. A sound so ordinary and so precious, it represents every gentle moment our species ever had. And maybe that's enough. Maybe the meaning isn't in being found. Maybe the meaning is in the sending, in the act of reaching outward, in the refusal to let distance or time or improbability stop us from saying we were here. We existed. We made music and art and science. We loved. We spoke into the void because silence felt impossible. The golden record spins onward a message we never expected anyone to hear. But the message was never the point. The point was the trying, the gesture. The refusal to accept that meaning requires an audience. We said hello. We sent our best. We cast our voices into the infinite dark. And that act, small, symbolic, nearly futile, might be the most human thing we've ever done. But long before the record finds its hypothetical listener, Long before it drifts within light years of another star, its journey will become something else. Not a message, not a mission, just a presence. A small, silent object carrying a memory of home, moving farther and farther from everything it was meant to represent. And in that motion, that endless purposeful motion through the dark, there's something that feels like a promise. That we reached, that we tried, that when faced with the infinite, we didn't stay quiet. We sent our voices forward, hoping someone might hear. And if no one ever does, at least we spoke. Right now, at this very moment, Voyager 1 is 15.3 billion miles from Earth. That number grows by about 38,000 miles every hour. By the time you finish listening to this sentence, Voyager has traveled another 300 miles farther from home than it was when the sentence began. It's moving away from us at a rate we can measure, but barely comprehend. And somehow, impossibly, we're still talking to it. The signal from Voyager 1 takes 22 hours and 52 minutes to reach Earth traveling at the speed of light. When Mission Control sends a command, switch to backup thruster, adjust antenna orientation, power down this instrument they're speaking to where Voyager was yesterday. When Voyager responds, they're hearing from where it was 2 days ago. It's not a conversation anymore. It's an exchange of messages across time, each one a small act of faith that the other is still listening. The spacecraft transmits at 23 watts. For reference, that's less power than the charger for your phone. By the time that signal crosses 15 billion miles, it's been diluted to about 1/billionth of a watt. The deep space network antennas that receive it are picking up a whisper so faint, it's barely distinguishable from the background radiation of the universe itself. And yet we hear it. Every day the antennas point toward the coordinates where Voyager should be, and every day the signal arrives. Faint, distorted, delayed, but there. The engineers who built Voyager are mostly retired now or gone. The mission has outlived many of the people who designed it. But new engineers have taken their place, learning the quirks of 1970s technology, learning to communicate with a machine older than they are. Some of these engineers weren't born when Voyager launched. They've spent their entire careers talking to something they'll never touch, maintaining a relationship with a machine that will die long before they retire. Why do they do it? Because the signal still comes. Because Voyager still speaks. Because as long as it does, we have a responsibility to listen. The spacecraft is running on fumes now, metaphorically, since there's no fuel in the traditional sense. The plutonium-238 in its power generators continues to decay, producing heat that's converted to electricity. But the heat output drops every year. The available power shrinks. Mission planners have been making hard choices. Which instruments to shut down first? Which can still produce meaningful data, which are redundant. Every few years, another system goes dark to conserve power for the rest. In 2019, they turned off one of the heaters for the cosmic ray instrument. The instrument now operates at minus 59 degrees Celsius, far below its design temperature. Engineers expected it to fail. It didn't. It kept working, kept measuring, kept transmitting data about the radiation environment in interstellar space. In 2023, they switched Voyager 2 to a backup thruster system because the primary thrusters were clogging after 46 years of operation. The backup thrusters hadn't been fired since 1980. Engineers weren't sure they'd still work. They did. The spacecraft keeps surprising us, keep exceeding expectations, keep surviving conditions they were never designed to endure. Scientists estimate that around 2025, possibly as late as 2030, Voyager will no longer have enough power to operate any instruments. The last data stream will stop. The spacecraft will go silent, at least in terms of scientific measurement. But even after the instruments die, Voyager will continue transmitting a carrier signal, a blank tone that says, "I'm still here," without sending any data. That carrier signal will persist for a few more years until power drops too low to sustain even that. And then nothing. The spacecraft will still be moving, still traveling at 38,000 miles per hour through the interstellar medium. But we won't hear from it anymore. The conversation will end not because Voyager stopped, but because it stopped being able to speak. How do you say goodbye to something that's been part of your life for half a century? The mission team has started preparing for that moment. They're archiving data, documenting procedures, writing final reports. They're planning a ceremony for when the last signal arrives, not a funeral exactly, but an acknowledgement, an honoring of what Voyager accomplished and what it meant. But there's also resistance. Some engineers refuse to think about the ending. They focus on maximizing every remaining day, squeezing every last bit of science from the fading power supply. They talk about Voyager in the present tense as if it will always be there, always transmitting, always just beyond reach, but never truly gone. Maybe that's healthier. Maybe grief can wait. Voyager's trajectory is set for the next several 100,000 years. In about 300 years, it will reach the inner edge of the Oort cloud, the spherical shell of comets surrounding our solar system. It will spend 30,000 years passing through that cloud, though the chance of actually hitting something is negligible. Space is empty, even when it's full. In 40,000 years, Voyager 1 will pass within 1.6 light-years of Gliese 445, a red dwarf star in the constellation Camelopardalis. It won't be captured by the star's gravity. It will just drift past a dark speck moving through the outer reaches of another star system. By that time, human civilization will be unrecognizable if it exists at all. Our current nation's languages, technologies, all will be as distant and irrelevant to future humans as the Stone Age is to us. Maybe more so. But Voyager will still be there, still moving, still carrying its golden record. In 296,000 years, Voyager 2 will pass within 4.3 light-years of Sirius, the brightest star in our night sky. Sirius is a binary system, two stars orbiting each other. Voyager will drift past, both unnoticed, a fragment of ancient history from a species that once looked up at Sirius and made it part of their mythology. The Egyptians aligned their calendar to Sirius's rising. The Greeks called it the dog star. In 300,000 years, Voyager will visit it carrying a record that includes ancient Greek greetings and Egyptian music. A loop closing across timescales we can't really imagine. There are people alive today who were alive when Voyager launched. They were in their 30s then. They're in their 70s now. They've watched Voyager's entire journey from the planning stages, through launch, through each planetary encounter, through the heliopause crossing to now. They've grown old alongside a machine. They've seen their children grow up hearing about Voyager. Some have grandchildren who know the spacecraft as part of family lore. Your grandfather worked on Voyager. When Voyager goes silent, it will be the end of a shared experience spanning nearly 5 decades. A mission that connected generations. That gave people something to look forward to, something beyond their daily lives. A reminder that we're capable of building things that outlast us. Isn't that what we all want in some way? To create something that matters after we're gone? The Voyager mission has produced more than 30 terabytes of scientific data. That might not sound like much by today's standards. Your phone probably holds more. But consider this. Is data from Jupiter's magnetosphere, from Saturn's rings, from Neptune's storms. Data about the heliopause, the termination, shocked the interstellar medium. Data collected over 47 years, transmitted across billions of miles, decoded and analyzed by thousands of scientists. Papers are still being published from Voyager data. Discoveries still being made. The mission scientifically ended decades ago, but the science continues. That's the nature of exploration. The journey generates knowledge that outlasts the journey itself. When the mission finally ends, when the last signal fades, NASA will likely decommission the Deep Space Network antennas currently dedicated to Voyager. Those antennas will be reassigned to newer missions, Mars rovers, asteroid probes, future spacecraft heading to the outer planets. but they'll leave one antenna pointed at Voyager just in case. Just in case some miracle occurs and the spacecraft finds power we didn't know it had. Just in case it speaks again. It won't. But we'll listen anyway, because that's what you do for something you love. You keep the door open even when you know no one's coming home. There's a strange comfort in knowing Voyager will outlive us, that long after our lives have ended, after everyone we know has died, after our civilization has transformed or collapsed, or evolved into something unrecognizable, Voyager will still be out there, still moving, still carrying our message. It's the closest thing to immortality we've ever built. The golden record contains a diagram showing Earth's location relative to 14 pulsars. Pulsars slow down over time as they lose rotational energy. By measuring the current pulse rate of these 14 pulsars, any civilization that finds the record could calculate how long it's been traveling and trace it back to its origin. But pulsars don't last forever. They slow cool, eventually stop pulsing. In a few 100 million years, some of those 14 pulsars will be dead. The map will become incomplete, harder to decipher. In a billion years, most of them will be gone. The map will be nearly useless. And yet, the record will remain still intact, still spinning through the dark, carrying a map to a place that might no longer exist in any recognizable form. Does that make the message meaningless? Or does it make it more poignant, a voice from the deep past, speaking to a future that has forgotten how to hear it? Carl Sagan died in 1996, 19 years after Voyager launched. He didn't live to see it cross the heliopause, didn't live to see the mission reach 40 years. He spent his final years knowing that Voyager would outlive him, would continue the work he started long after he was gone. In one of his last interviews, he said, "The spacecraft will be encountered and the record will be played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. The hope isn't in being found. The hope is in the sending." Anne Druyan-Sagan's widow and collaborator on the Golden Record Project said in a later interview, "Every time I think about Voyager, I think about the people who built it, the people who are still tracking it, the people who will never know what happens to it. And I think about how much love went into it. Not romantic love, but the love of doing something right, the love of reaching beyond yourself. That's a kind of love we don't talk about enough. Love as reaching. Love as effort across impossible distance. Love as the refusal to let silence win." The Voyager mission cost about $865 million over its lifetime, less than the cost of a single modern stealth bomber. For that price, humanity sent 2 machines to 4 planets, discovered new moons, measured interstellar space, and created a message that will outlast our civilization. What else could we achieve if we decided reaching mattered more than territory? If we spent our resources on understanding rather than control? Right now, Voyager is sending back data about the density of the interstellar medium. It's measuring cosmic rays. It's detecting plasma waves, oscillations in the charged gas between stars. Scientists use this data to understand the local galactic environment, to map the structure of space the sun is traveling through. This information is practical, useful. When we eventually send humans to other stars, if we do Voyager's measurements, will help us know what to expect, what radiation levels to prepare for, what densities we'll encounter, how interstellar space actually behaves versus how we modeled it. Voyager is scouting ahead, mapping the frontier, sending back reports from the edge of everything we've touched, saying here's what it's like, here's what you'll face, here's what's possible, and we're listening. Taking notes, planning, because the journey doesn't end with Voyager. It begins there. There are proposals for future missions, interstellar probe, a spacecraft designed specifically to reach 1,000 AU, far beyond where Voyager has gone. Breakthrough Starshot, a project to send tiny light sail probes to Proxima Centauri at 20%, the speed of light, reaching the nearest star system in 20 years rather than 73,000. These missions are ambitious, expensive, uncertain. They might not happen, but they exist as ideas because Voyager proved it's possible to leave, to survive the journey, to keep transmitting from distances that seemed impossible. We know now what we didn't know in 1977, that we can build machines that outlast us. That exploration doesn't require return. That sending something farther than we can follow is not futile, it's foundational. When the last Voyager signal arrives, there will be sadness. But there should also be gratitude. Gratitude for 50 years of data, for images that changed how we see our place in the universe, for proof that we can reach beyond ourselves. And there should be resolve. The resolve to keep reaching, to build new Voyagers, to send new messages, to continue the conversation even when no one answers. Because the meaning was never in the reply, it was in the speaking. Voyager is still out there, still moving, still carrying a piece of 1977. Earth, a time capsule from a world that no longer exists in exactly the same way. The people who built it are older now, or gone. The technologies have advanced beyond what they imagined. The Cold War that shadowed its launch has ended. The world has changed, but Voyager remains unchanged, still carrying its golden record, still transmitting its faint signal, still speaking into the dark, patient and tireless, asking nothing, offering everything. And we're still here pointing our antennas toward the place where we know it should be, still listening for the whisper across the void, still refusing to let distance mean the end of connection. Because that's what exploration is. Not arriving, not conquering, not claiming. Exploring is reaching, is trying, is sending something forward and trusting it will matter, even if you never see where it lands. Voyager taught us that, and the lesson continues growing quieter each year, but never quite silent as long as we choose to listen. Sleep well, friend. Dream gently. The stars are still there. The spacecraft still flies. The message still travels. And somewhere impossibly far away, a machine we built is speaking our name to the darkness. Thank you for drifting with me through this long, quiet journey, for letting me share what Voyager saw, what it means, and why it matters. These stories of planets and storms of rings and boundaries of photographs and golden records, they're a part of our collective memory now, part of what we carry forward. If you found something here that moved you, that helped you see differently, I hope you'll return. There are more stories waiting, more quiet nights, more reasons to look up and wonder. Until then, rest well. The universe is vast, but you're exactly where you need to be. Good night.